The title of this presentation is Probabilistic Programs in FIGARO and Quantum Error Correction. To begin with the presentation overview, we'll be introducing several applications of probabilistic programs in machine learning. And in providing this introduction, we'll be describing several open source probabilistic programming packages and libraries. And this will allow us to focus our attention towards one probabilistic programming open package or language, FIGARO, which has connections with compiling quantum circuits. And we'll want to demonstrate why quantum circuits are a central object of interest to study in quantum computing by motivating the significance of quantum error correction. And we'll come full circle with all of the notions between all the common notions that we can make sense of between probabilistic programming, quantum circuits, and quantum error correction by discussing notions from probabilistic programs and quantum error correction together. So we'll first begin with a couple of overviews of papers from the slides to demonstrate connections between probabilistic programming, machine learning, quantum computing, and quantum error correction, and how these fields, although they may appear a little bit disparate or separate, they actually have many commonalities and features together. And a lot of the difference mostly probably comes from a language barrier, because a lot of what people try to think about in terms of statistics and machine learning and enforcing priors on data and looking at how distributed or narrowly distributed data can be, or in confidence intervals, and relating how data is and being able to perform inference, in essence, actually has a lot to do with how states are instantiated in time evolved in quantum circuits and quantum computing, and how errors can unfortunately propagate and accumulate in undesirable fashions, which we can look to mitigate and really prevent from happening using error correcting schemes and error correcting codes. So the interest between all these fields comes from the fact that there are many different types of papers, either relating more to biological focus, which relate to the fact that machine learning and probabilistic programs can help us have enhanced prediction for either searching for different types of mechanisms that can be related to how diseases can start and initially infect a host organism and perform this process of replicating and amplifying its genetic material into the host that it's trying to invade and infect. And this can also be related to the fact that machine learning can help us perform better types of predictions for how vaccination responses can be amongst different individuals, and how this has to relate to the formation of different types of follicles, or different types of matter within the body that can help the disease propagate further than what is initially intended or what someone would expect. But as we're going more away from the biological focus, there can also exist other types of notions of robustness, whether it be a robust neural network for being able to build up some resistance to corruption and corrupt training data, and how the network would still be able to perform well under certain classification or training tasks from training data that isn't exactly as good, or exactly wouldn't encapsulate all the information from a training data set that one would like to feed a machine learning model. And this is also given from the fact that machine learning and robust neural networks and other types of related networks can be used for trying to perform some type of genome annotation or cell annotation, which can help us try to predict what types of cells could become or could be more prone to infection in a diseased individual. And continuing along our introduction before getting to probabilistic programming and quantum computing and quantum error correction, we can look at there do exist papers and references within the literature which more relate to being able to leverage machine learning, as demonstrated in the first reference here, for assessing market level food safety and the probability of some infection occurring in some type of open market environment where a lot of infections or maybe certain products aren't necessarily kept as clean as they should have, and could have led to an outbreak of a different type of disease like COVID or maybe other types of respiratory diseases. And this is relating to the fact that also quantum computing and quantum error correction, they can be made of as valuable fields which can find applications in supply chain management and optimizing operations rather than just the biological focuses or the pharmaceutical applications that we have been discussing in the previous slides. And as we're getting more towards defining what a probabilistic program is and the connection that it has with quantum circuits and time evolution, we can see that it's also of interest from several papers in the literature to determine the circumstances under which different types of networks can continue to generate reliable predictions and whether there will be any statistical bias that we can try to quantify or estimate during different types of training procedures if the model is a supervised model, and how we can mitigate this type of error, which would help improve our inference and classifications circumstances or tasks that we want in other circumstances that we want to use this model for. And local error correction has found its way into several applications of machine learning and probabilistic programming because it can enhance, as demonstrated in the first paper reference, the detection of topological order, as well as other related characteristics in which scientists, both in academia and industry alike, have been looking at different ways to build and synthesize quantum devices, which can try to mitigate local errors by very precisely controlling local degrees of freedom and other properties of quantum mechanical particles that we initially use as our building blocks for a larger scale or more fault-tolerant quantum computer, which we hope can be synthesized in future generations for use. And a lot of this has to do with the fact that many properties of these particles have to be controlled very precisely, from the angular momentum to the regular momentum to the charge, as well as to how these devices are actually put together and synthesized, which I'll draw some reference to from some equipment that's been in production and development at Google Quantum AI. And we can introduce probabilistic programming by first discussing one such open source programming and discussing how this relates to other open source libraries for probabilistic programming to make our way towards quantum computing and quantum error correction. First, we can look at Edward, which is a library for probabilistic modeling, inference, and criticism. And from the documentation that's given on the website, the developers of Edward, they draw our attention to its potential uses, including supporting modeling and directed graphical models, as well as looking at neural networks, which relate to layers and instantiating all these objects for training and other types of manipulations in Keras, as well as making probabilistic programs and looking at other types of generative models. And as we have mentioned, there can also be several types of applications of variational inference, whether it be related to, as we have mentioned, trying to look at behavior supply chains and operations optimization, as well as looking at different biologically oriented aspects from drug discovery to molecular dynamics and quantum chemistry. But rather than Edward, there are several other types of probabilistic programs which serve a similar type of interest. In one of the presentations that was giving at PyData, which was some conference that they had in the UK from last year, one of the speakers gave a really great list about several different types of probabilistic programs and the commonalities between all of them, which can help us open up our perception and our minds to quantum computing and quantum circuits, and how essentially a quantum circuit is in essence a probabilistic program, which can be viewed from the fact that one of the open source probabilistic programming libraries that we can look at directly bridges the gap between quantum computation, quantum circuits, and probabilistic programs and probabilistic circuits, and how to compile results from these probabilistic objects for making meaningful conclusions, like the types of purposes that we have mentioned for Edwards in the previous slide. So this just demonstrates that all these types of programs like TensorFlow probability, Edward, MC, Pyro, NumPyro, Python, Monte Carlo, and PyStan all together can enhance our ability to manipulate random variables which are generated in these open source Python libraries, and how, in essence, this really reflects a lot of type of natures and characteristics of quantum mechanics, because we don't have infinite precision of the momentum and the position of a particle simultaneously. And this is where the probabilistic room in the probabilistic framework comes into play. And this is just to show that for FIGARO, which is the specific probabilistic program that's of main interest for us, we can instantiate quantum circuits which can be directly mapped onto quantum circuits that are either made in Qiskit or in Cirq, where Cirq is the open platform, the open source Python library provided by Google, and Qiskit is the open source counterpart for making quantum circuits provided by IBM through the FIGARO chain object. FIGARO is an open source probabilistic programming language that's provided by Charles River Analytics, and it's a free open source probabilistic programming language for probabilistic modeling. And the main aspect of the chain object that we can make use of and exploit for making connections with quantum circuits in Cirq is that we can initialize every one of the registers of the quantum circuit through the FIGARO chain object, and we can perform time evolution of this quantum circuit through the FIGARO chain object, and then we can extract measurements after performing some fixed number of repetitions of the quantum circuit, which will then allow us to make different types of comparisons from open, or like open source on the cloud quantum devices and quantum computers for error rates, and how we can potentially mitigate such error rates through different type of error correcting codes, and how the composition and strategies of these error correcting codes would differ as we scale up our quantum device to the number of qubits that are more realistic from current devices like at IonQ or Google Quantum AI that we'll describe a little bit further. And this is a slide in which we're going to demonstrate a lot of the types of characteristics of hardware that appear in quantum computers from Google Quantum AI. In particular, we can see on the right-hand part of the slide that we have the chip, which is a Sycamore chip, which is given by the fact that it's synthesized with 54 qubits. But even though it has a little more than, or 52 qubits, I think, but even though it has a little more than 50 qubits on the chip, actually only 12 or 13 of those qubits are typically used for performing the computation. So it's just demonstrating that a fundamental limitation of having this type of probabilistic computation through quantum computing is arising from the fact that even if we have some type of reservoir of qubits, like 52 qubits on the Sycamore chip, we're not actually able to use 100% of the qubits that are available on the Sycamore chip for scaling the computation. We can only use barely 25% of the total number of qubits, which are then used together across multiple chips to build up the types of quantum computers that Google AI has been looking at, or Google Quantum AI. And on the left-hand side, this shows a bottom-up view of a dilution refrigerator, which is used by Google Quantum AI, which is of interest for testing either future types of algorithms like the variational quantum algorithm that I've looked at more extensively, along with other people in the McMahon lab at Cornell, and how this performance can be related to running the algorithm and looking at how well the algorithm would perform on different types of open source quantum devices. And this is just to demonstrate some type of quantum circuit diagrams, which is bridging the gap between the probabilistic programs in FIGARO, and how from these probabilistic programs through the chain object, we can initialize different components from the registers of the quantum circuit, and how we would like to perform time evolution to extract some type of measurements from readout along some fixed number of subsets of the quantum circuit. And this is given by the fact, like from the quantum circuits that we can either define in Qiskit or in Cirq, that we can see that on the left-handmost side of this quantum circuit, we start out by initializing the state of these 4 qubits, and they each undergo a Hadamard transformation followed by other Pauli rotations, which are given by the blocks which appear in the first 2 columns of the quantum circuit. We can see from the second register that after we perform another Pauli operation, we can have a swap operation between the topmost register and the second register, before which another Pauli operation is executed, as well as another swap operation. And we can see that the remaining parts of the circuit are performed by looking at either other combinations of poly operations as well as other combinations of swap operations, rather than just swapping the first topmost registers of the quantum circuit. We can also swap the topmost and the bottommost registers of the quantum circuit, and so on and so forth. And this is demonstrating that on the online resource, which IBM has, which someone can use to run different types of elementary quantum circuits for determining the error rates, we can see that from like a type of IBM device, we can see that their circuits, which one can drag and drop and paste within their online editor, which gives access through some credits to actual quantum devices, can be used for determining what are the error rates of the 2x2 qubit operations, which is going to fundamentally determine what would be the error of a larger device as we scale up the number of qubits. And this is just to say that in another presentation, I've already discussed more components of the quantum circuit, which come into play for the variational quantum algorithm, which is of interest to further investigate other related types of algorithms to the variational quantum eigensolver, and how these different types of characteristics of the VQE and the VQA can also be related to probabilistic programs through defining quantum circuits and time evolving these circuits and looking at the related chain objects in FIGARO and how this relates to different types of probabilistic programs, and how essentially the probabilistic program and the quantum circuit and the quantum error correction all reflect different types of aspects of the same underlying phenomena, which we are physically constrained with through quantum mechanics, and how this can be used in the future to try to test out different types of algorithms and their performance, and whether the algorithms would give any type of speed up. So conclusions is that we developed connections between time-evolving quantum circuits and probabilistic programs, and we motivated the significance of quantum error correction for preventing errors from propagating on quantum computers, because that's unfortunately probably a point that many mainstream publications don't actually present in the most straightforward way, which is that quantum computers, if they're scaled up, can be very much subject to different types of decoherence in T1 and T2 time relaxation errors, which can really mess up and completely ruin the type of information that we want to read out from the wave function, which is relating to the type of performance of the algorithm that we would hope to obtain some speed up on. And finally, we drew attention to the error rates of 2-qubit operations, which are the fundamental error rates for larger qubit systems, which are being developed commercially and academically for future use. And thanks for watching.